Hi there. Today I'll be giving a talk about our recent work on the complexity of a unique witness. And this is joint work with Anurag Anshu, Jonas Haferkamp, and Quinn Nguyen. So the principal question that we want to study in our work is whether verification can be done uniquely. In the classical setting, this was originally studied by Valley and Vazirani, and in their paper, MP is as easy as detecting unique solutions. They show that MP has a randomized reduction to unique MP, and in particular, they can reduce from SAT to unique SAT. The key tool that they utilize in their paper is the isolation lemma, and the principal idea is just to apply a random hash function to the set of satisfying solutions to your original SAT instance. If you have a very large field of solutions represented by these dots, then they show that if you apply a random hash function, then with high probability after doing this procedure, you'll be left with a single unique witness. On the other hand, the story is not necessarily so simple. In particular, in 1998, Bagel, Berman, and Fortnow, they showed in their work MP might not be as easy as detecting unique solutions, that there actually is a oracle separation between MP and unique MP. So even though if you allow randomized reductions, then MP can be viewed as morally equivalent to unique MP, the story isn't so straightforward, and there is a bit of subtlety when you're discussing these two classes. However, most people view, at least classically, as the work of Valiant and Vazirani resolving this question, and more or less you should think of MP and unique MP as being comparable or like exchangeable classes. The question we want to study in our work is whether the same thing can be done quantumly. This was originally posed as a question by Haranov et al. In 2008, and the authors were wondering whether a similar procedure, this randomized projection procedure, could work for unique QMA as well, from QMA and unique QMA, which are the quantum analogs of MP and unique MP. There, in the quantum setting, the nice analog of a randomized hash is maybe a random projection. So you take your original quantum witnesses, which are represented by some states in some ambient space, and then you apply a randomized projection onto your states, and then you accept if both your original verifier and this projection accept your witness. However, they notice that this transformation does not actually create an inverse polynomial gap. It doesn't sufficiently distinguish good instances and maybe second to best instances. And instead, most states will be accepted with probabilities exponentially close to each other. This is partially due to the concentration of quantities like this expectation under projections of trace pi psi. So trace pi psi is just measuring the overlap between psi and your random projection. And quantumly, it turns out with very high probability over these pi's and any two states, psi and phi, the overlap between psi and pi and phi and pi will be roughly the same. As a result, these randomized projections aren't enough to distinguish different witnesses. So this seems to imply that for arbitrary states, a unique verification procedure might be a bit difficult. However, and because of this fact that it's difficult for arbitrary states, we're able to leverage this into an oracle separation and formally show what Haranov et al. Hinted at in their work. Our first theorem states that if for a classical oracle, there's a classical oracle relative to which unique QMA is not contained in QMA. And similarly, if you allow yourself quantum oracles, we can actually show something a bit stronger and show that BQP to the unique QMA is not contained in QMA. And now this is really the kind of the flavor of the result that we want to show, because if you recall, for Valley and Vazirani, they show a randomized reduction between these two classes, between the classical analogs of these two classes. And so our theorem 2 is really ruling out a black box analog to Valley and Vazirani in the quantum setting. However, one thing to notice is that really we don't care about unique verification for these arbitrary families of states, and in the end we want to understand what happens to ground states of these local Hamiltonians, which are the quantum analog of classical CSPs. And this family of states, ground spaces of local Hamiltonians, it feels a lot more structured, and it seems like there should be some kind of structure that we can leverage in order to construct a isolation procedure. And in particular, actually, with this additional assumption of structure, we can actually show a isolation procedure. And our theorem 3 states that under plausible physical assumptions, there exists a isolation procedure for low energy eigenstates of local Hamiltonians. And as a result, we can show that there is a unique verification procedure for algorithms for problems in QMA. So, as an outline for the talk, I'm going to start with some background on just like quantum things, and then I'll describe some tools and techniques for our oracle separation. Then, moving into the algorithmic section of the talk, I'll introduce a key physical assumption that we'll need, which is the eigenstate thermalization hypothesis, or ETH, and then give an overview of our unique verification procedure. So let me begin with some background. A quantum verifier is a circuit composed of layers of unitary operations. A unitary operation is just is represented by a unitary matrix, which satisfies the property that like U dagger or U conjugate transpose is equal to identity. So this captures the notion of quantum being given by reversible operations. Additionally, there'll be and finally, your output of the quantum verifier is given by some final measurement that you take. So this would, in general, be some kind of projective measurement. Then the important complexity classes are QMA. A language L is contained in QMA if there is some uniform family of quantum polynomial time verifiers, such that in the yes case, there is some quantum witness which causes your verifier to accept with probability at least 2/3. And in the no case, if your string is not in the language, then for any witness, your verifier should reject with, again, the same probability. So this really is the quantum analog of MP, where rather than a classical verifier, you have a quantum one, and instead of a classical witness, you have a quantum state. Unique QMA is defined similarly, but in the yes case, we also have the further restriction that there should be a unique witness that causes your verifier to accept. The idea of uniqueness is maybe a little bit more subtle in the quantum setting, just because these are not necessarily discrete objects. But you should think of this as saying that there is a unique vector which causes your verifier to accept, and for any other vector or witness orthogonal to your good vector, your verifier should reject with probability at least 2/3. Additionally, another important idea is these like oracularized complexity classes, QMA to the O and unique QMA to the O. These are defined similarly, but now we allow access to some arbitrary oracle or unitary O. So pictorially, what's going on with all these pieces put together, we have some auxiliary registers, which are like computation registers, as well as the input register for the input witness. And then your quantum circuit is given by this alternating sequence of oracle of unitary gates, as well as controlled access to your oracle. So the unitary gates here are given by UI, and then O is again the oracle. Finally, you perform some output measurement on your output qubit and return the result. So let me just talk a little bit more about this oracle model that we're considering, because there are some interesting details associated with it. We should think of O as abstracting some black box access to an unknown quantum object. So a kind of prototypical task that you might encounter in QMA to the O might be given access to the ground space of some unknown Hamiltonian, or you can think of this as the given access to the accepting space of some like quantum CSP. You want to decide whether the dimension of the accepting subspace, or degeneracy, is smaller than K1 or bigger than K2. So O here should be some quantum unitary or some unitary that gives you access to this ground space. This is kind of interesting because often when you're talking about oracle separations between classes, the gold standard for an oracle separation is given by a classical oracle. So in particular, one which is defined by a classical function, maybe mapping Boolean strings to 0, 1. However, for these kinds of tasks, it really makes a lot of sense. It makes a lot of sense to define our oracle O as being a quantum object, because in general, the ground space of a unknown Hamiltonian, it won't be classical. It'll have some like crazy structure, And really, the most general thing we can say is that it's going to be some subspace, and therefore the best access we have to this is via a quantum oracle, which is some operation on quantum states. Formalizing this previous example, we can define a nice task to consider for our separation between unique QMA and QMA. Formally, we define the problem, quantum approximate dimension, which is parameterized by K1 and K2. Here, we take some subspace of C2 to the n, and promise that either S has dimension at most K1 or at least K2. You want to decide which of these two is a case. Of course, if S is like a classical subspace, so maybe it's spanned by like Boolean vectors, then it makes sense to think of access as coming via a classical oracle. But in general, S is just some subspace of C2 to the n. Then our oracle provides access to S via the projection onto S. In particular, we define O as being equal to identity minus 2 times the projector, so this acts as the reflection about S. So if you feed it a quantum state outside of S, it will act as identity. If you give it a state psi, which is in S, then it will act as a phase flip. For our separation between unique QMA and QMA, we'll only need a version of this problem for K1 equals 0 and K2 equals 1. So all you want to decide is whether your subspace is empty or non-empty. Now, how do we actually formulate a separation between unique QMA and QMA? Well, we need to show two things. The first is that for any S, there is some QMA oracle, oracular QMA oracle, QMA verifier, which decides QMA, Q approx dimension 0, 1. On the other hand, the second task we need to show is that for many S's, there is no actual oracular unique QMA verifier. And then via a standard like diagonalization argument, we can take this and translate it into a decision problem, which acts as a problem which is contained in QMA to the O, but outside of unique QMA to the O. Now, let's observe one quick thing, which is that the first point actually is pretty easy to show. In QMA, we don't need the witness to be unique, and so the natural witness to provide, the verifier, is just any state psi in the support of S. Then the QMA can do the QMA verifier can check whether S induces a phase flip or not on psi, and use this to decide the problem. Intuitively, the reason why this is actually difficult for a unique QMA, on the other hand, is that there are many possible candidate witnesses, especially when the subspace S is quite large. If S is exactly dimension 1, then it's easy, but if S is like super polynomial, then there are many different psis that you can imagine giving to the oracle, giving to the verifier, and it's hard to formulate a procedure which isolates a unique one. However, we show that this is actually indeed possible. The overall idea for the proof is the following. Imagine that you have a very large subspace T. So here, the dimension of T is like some 2 to the Cn, for C being smaller than 1. And now let's consider some decomposition of T into S and delta. You should think of S as being dimension 1 and delta as being some dimension K thing that contains everything else. And then the acceptance probability of any verifier which queries this reflection oracle OT on input psi is essentially given by the overlap between psi and pi s and the overlap between psi and pi delta. This is sweeping a lot of details underneath the rug because, of course, the verifier can perform unitary transformations on psi and then query the oracle, but this will be enough to get the flavor of the proof across. Our task now is to show that the intersection between psi and pi s, where pi s is a small part, and psi and pi delta, where delta is a large subspace, both of these quantities are small. For this second quantity, this will turn out to be the easier one. The way we show that this is small actually goes back to what we talked about earlier, where we observe that the reason why a unique verification procedure for QMA is difficult is that random subspaces have very small overlap with psi, or that this quantity concentrates very well. As a result, if you imagine that we initially first fix an S and then like look at random extensions of S into T, so now T is some random variable, then these intersections between pi delta and psi are going to be very small. As long as delta is not too big, then in fact the intersection between pi delta and psi is going to be pretty much the same for any pi delta. As a result, if we do this sampling procedure, we can actually bound the second quantity very well. Now, what about the first term? The first term is a bit more difficult, and we can't make the same argument because it will turn out that psi is related to S. Like, essentially, because we're building these subspaces T off of S, then we should think of psi as being some function of S. For this, we take a slightly different approach. Let's fix the T, and then consider any decomposition of T into S1, O plus S2, ... Sk plus 1. So this is like the direct sum of k plus 1 one-dimensional subspaces. And now we ask ourselves whether whether all of these SIs can have actually the same witness psi. And the answer is no, for the following reason. If psi is a good witness for Si, this means that psi morally has good overlap with pi Si. However, all of the SIs are orthogonal, and as long as we pick k to be sufficiently large, then this like unit 1 vector, this norm 1 vector psi, can't have good overlap with every single one of these psi i's for k many of them. As a result, we'll be able to fix one of these SIs which have this small overlap and take it to be our original S. And with this procedure, we can also bound the first one as well. Again, this is missing a bunch of different technical details, but for full details, please consult our full paper. One nice thing we can do is extend this result to BQP to the unique QMA. And in some sense, this is like the more interesting part of the paper. In order to do this, and the reason why it's more interesting is that it's like an actual analog, or it rules out an actual analog to a quantum version of the Valley and Vazirani procedure. To do this extension, to lower bound this, to construct a separation in this setting as well, we need an additional tool, which in our work we call the circuit polarization lemma. Morally, we need this lemma for the following reason. A verifier that's in a BQP to the unique QMA verifier is a BQP algorithm, a quantum polynomial time algorithm, which is allowed to make oracle queries to a unique QMA oracle. One thing we'd like to do to finish the proof is argue that whenever the verifier V queries a unique QMA oracle, it's essentially asking it to solve a smaller version of our problem, and therefore we can port over our previous result onto one of these individual calls to the unique QMA oracle. However, this isn't exactly the only mechanism by which this verifier could work, right? You can imagine that the verifier actually only wants to make a little bit of progress on each call to the unique QMA verifier. Unique QMA oracle, and therefore we can't actually translate any single call into a lower bound, or we can't actually apply a lower bound to any single call. However, our circuit polarization lemma says that for any circuit making polynomial queries to a subspace oracle O, the acceptance probability is going to concentrate about 0 or close to 1. And what this means is that we can leverage this lemma to show that there's going to be at least one call that the outer verifier makes to the unique QMA oracle, which is essentially a solution to the full problem. At some point, the outer verifier needs to show its hand and really just ask the unique QMA oracle to solve the problem for it. And with this lemma in hand, we're able to apply our previous unique QMA lower bound against the verifier's calls and achieve a separation between BQP to the unique QMA and QMA. Finally, I'm going to conclude the talk by discussing very quickly our isolation procedure from a structural assumption. So before I begin, just at a high level, our previous results again rule out a black box isolation procedure. Black box here in the sense that you just get black box or oracle access to some arbitrary subspace and you don't have any structural assumptions about the subspace to work with. However, in general, local Hamiltonians are very structured, and therefore it seems like there should be some tools we can leverage. The two important techniques that we'll use for our work is this quantum expander test of Aharonov et al. And this quantum expander test allows you to uniquely verify the maximally entangled state under the assumption that you have a appropriately mixing operator within the subspace that your entangled state is defined on. So given some subspace, you can uniquely verify the maximally entangled state on that subspace given the existence of this operator. And so really the hard part in applying this expander test in our setting is going to be defining these mixing operators. Because a natural version of this quantum expander test would be to apply it to the low energy subspace of our Hamiltonian, but naively, it's not clear what the analog of a mixing operator is for this low energy subspace. Fortunately, there's a very nice physical assumption that we can make here, which is called the eigenstate thermalization hypothesis. And it says that if you fix some Hamiltonian H, or maybe a family of Hamiltonians, there exists operators A1 through AM, such that for any eigenstate psi of your Hamiltonian with energy lambda, then the state AI psi, so AI applied to psi, it's also mostly supported on the eigenstates with energy lambda. So you can think of these AIs as being approximately diagonal in the eigenbasis of the Hamiltonian psi, except for there will be some fluctuations in the off diagonals, which will allow us to define mixing operators. This version of ETH that we'll use, we actually call it the computational version of ETH. It's quite nice, and ETH by itself is a fairly plausible physical conjecture. It's expected to hold for many physically relevant Hamiltonians, such as the famous SYK model. Additionally, many physical quantum systems have been experimentally validated to show this behavior. Pictorially, what does this look like? Well, the ETH assumption says that for an operator AI, if you look at this delta size energy window around a specific energy lambda naught, then we'll have these fluctuations on the off diagonals, which are going to be standard Gaussians, and the constants in the middle are going to be functions. These values in the middle are going to be functions of A as well as the specific eigenstate that it corresponds to. But really, this ETH assumption says something about what this local region around a particular energy value lambda naught looks like, rather than saying some global statement about the operator A. As a result, to apply this ETH assumption, what we'll need to do is sandwich these AIs with approximate projectors pi delta onto this energy window. We can do this by using essentially a quantum phase estimation procedure to narrow down and project onto this energy window. This by itself isn't sufficient, because although there is some inherent randomness in these objects, we also need to show that there is some bound on the spectral gap on these operators in order to ensure that this mixing behavior happens quickly enough to give a polynomial time verifier. However, with all these tools put together, these operators AI suffice to form a sufficiently mixing family for our Hamiltonian, and allow us to construct a verifier, a unique QMA verifier for problems in QMA. To conclude, we've shown several things. Our oracle separations show that strict analogs of Vallée and Vazirani, as well as Stockmeyer's approximate counting, do not exist quantumly. On the other hand, we should view this as morally saying that any quantum analog should leverage the underlying structure present in local Hamiltonians. And with such a structural assumption, in our case using the eigenstate thermalization hypothesis, we are able to construct a isolation lemma. In a sense, if one believes that unique QMA is not equal to QMA, then this suggests that physically relevant Hamiltonians are not QMA complete, which would be, good news to physicists everywhere. That's it for this talk. Thank you for listening.